Hi, everybody. Thank you for coming back. This is lecture 8, and we're going to continue with some of the concepts we talked about in the last lecture, and we're going to continue with the concept of linear regression and the coefficient of determination. The coefficient of determination is very much related to the correlation coefficient, but with a slightly different meaning. So let's remember what we talked about as far as correlation. We have the measure. Correlation is the measure of the strength and direction of a relationship between two variables. It's represented by the correlation coefficient, the letter R, which ranges from -1 to +1, and it indicates whether variables tend to move together in a positive or negative correlation or have no relationship at all, which would be no correlation. And the sign, positive or negative for R, indicates whether or not the correlation is positive or negative. So when R is negative, we have a negative correlation. When R is positive, we have a positive correlation. Now, the closer R is to -1 and 1, the stronger the correlation is. So an R of -0.99, for example, -0.99 would be a strong negative correlation, and an R value of +0.95 is a strong positive correlation. And let's look at two other R values. Let's look at negative -0.15. That's pretty close to 0. And so that is a weak negative correlation. And +0.25 is also not very strong. It's not close to +1. So we say that's also a weak correlation, but this time weak positive correlation, +0.25. Okay, so the appearance of a positive correlation moves upward from left to right. The points tend to move upward from left to right. The appearance of a negative correlation, the points tend to move downward from left to right. These are screenshots from what we arrived at our calculator with our calculator at the last lecture. We measured the relationship between FEV1 and height. FEV1 was forced expiratory volume in 1 second. This was from a sample of 20 male medical students, and we measured their height and FEV1 values. And we had 20 pairs of numbers for X and Y. We put them in our calculator and we ran ln reg AX plus B. We got the output shown here. And then we also graphed those points in a scatter diagram, and we got the appearance of these points in the bottom picture there. R, the correlation coefficient, came out to be +0.58. So not too close to +1, but also not too close to 0. It's kind of in the middle. And the scatter diagram does confirm that there is a slight positive correlation. Okay, so this set of values doesn't appear to be too strong. We don't see all the points clustered close together, forming a perfectly straight line. So we're not at a strong correlation, but it is a positive correlation. Okay, and 0.58 seems to be a reasonable R value for points that look like this. Definitely moving upward from left to right, but not quite terribly strong. So regression analysis is what we're going to do next with R values. Correlation measures the relationship between the two variables. So it measures the strength, and that's what we get when we look at the R value, the strength of the relationship between the two variables. Regression analysis builds on this model and predicts how one variable affects the other. Okay, so how one variable affects the other. So what we have with correlation and this last example we were working on is we see that we have a relationship between height and FEV1. Okay, we know the strength of that relationship by looking at the value for R. But when we take this a step further and do a regression analysis on it, we will have the ability to predict the FEV1 for a male of a given height. So we only have 20 men in this sample, but if we use our sample data to create a model for prediction, we could use that model on any male by plugging in the male's height and getting out a predicted FEV1. So for any correlation, regression analysis allows us to predict the dependent variable given an independent variable. So in other words, we are going to predict the y given the independent variable, which is the x. Predict y given x. And we're going to do this by creating a linear equation. Linear equation is the equation of a line, and the line that we create is going to pass through the points of our scatter diagram so that it's spaced in a way where some of the points are above the line. So see, these points up here are above the line, and these points down here are below the line. And the line is kind of passing through the center of the points. It's called the line of best fit because it fits the points right through the center. And in the equation of a line, every single point on this line has an x piece and a y piece. I'm sorry, I just wrote the y piece when I meant to write the x piece here. The horizontal component is the x piece. The vertical component is the y piece. So what we will be doing in our predicting in our model to predict, we will be plugging in a value for x and we will be getting out a value for y. So we are going to put in the independent variable's value and get out the dependent variable value, and that would be our prediction. So how can a line be a predictor? This is more of the same here. The horizontal axis, the independent variable is height. So let's remember what that means in this example. Height is placed on the horizontal axis. The dependent variable, FEV1, is placed on the y-axis. FEV1 goes vertically. So we can make an estimated prediction about a male's FEV1 if we know his height. So using algebra, we plug in an x value into the linear equation, and we will output the estimated y value, the FEV1, that corresponds to that height. So imagine that we plug in the x at this location. So imagine right here, this x, we plug in this x into the equation, and we will get out the y at that location. Okay, and that would be the FEV1, that would be the prediction. So the way we do this, let's go back to the output of lin-reg. We do this by creating the equation of a line, and the equation of the line that we're going to be produced is in the form y equals ax plus b. Now lin-reg gives us the value of a and the value of b. X stays as a variable in the equation of the line, but a and b are constants. We're going to pull them out and round to 4 decimal places. So pulling out a, we have 0.074, and the reason why this is a 4 here is because we have an 8 after the 3, which makes us round that 3 up to a 4. And with b, negative 9.190, and again, we have an 8 here, so round this 3 up to a 4. Negative 9.1904. Oh, it looks like I have a small error here, so this should be 0.904. Okay, we're going to use the formula for an equation of the line and plug in the A and the B values. So look at what we have here. 0.0744 for A, negative 9.1904 for B. The equation of this line is y equals 0.0744x plus a negative 9.1904. We keep the x as a variable for the equation of the line. And that is the regression equation. We're not done using it yet. After we find it, we're going to put it into the calculator and see what it looks like among the points. So we're going to press y equals, and I'll do this with you right now. Let me share my calculator. Okay, remember that this is what our graph looked like. Now I'm going to press y equals in the top right, top left, sorry, top left. So I'm not going to do second stat plot. I'm going into y equals now. This is where we go to enter equations. So there's several equations or spots for equations that you can enter here. I'm going to enter it in y1. Okay, and we're going to put the ax plus b part of the equation right here. So remember that the A was 0.0744. And then we're going to put in the x variable. The x variable is the key that is to the right of alpha. And then we're going to, you know what? let me do this two ways. I want to show you that you can do plus and then a negative 9.19. Let me go back to what that was. 9.1904. And I'm gonna graph this, but I'm also gonna show you that it will be the same thing as typing in 0.0744x minus 9.1904. So with the equation graphed here or entered here, we're going to graph it by pressing the graph button. Okay, and that line is the line of best fit. That's the regression equation. Okay, now just to prove to you that it can be entered with a minus sign right here, if you want, you can change this plus negative to just minus, and then get rid of that negative. That is the same thing, and the graph appears in the same exact way. So note the location of the line. Note that it's not far above all the points or far below all the points. It goes right through the points. And that's exactly what we see with a regression equation. The line best fits the points. Okay, so there's the equation of there's the graph of our line. Here's the equation of our line entered in the calculator. And now we're going to make a couple of predictions. These are ways in which we can use our line to answer questions and make predictions for values that are not part of the sample. So imagine that we have a male who is 177 centimeters, who is not part of this study. Let's make a prediction on the estimated FEV1 value for that male. Okay, so we have the height, which is the X value, and we want to find Y, the FEV1. So the way we do this is through plugging in a value in for X in the equation and getting out the Y. Let's do the same thing again for a different height, a male this time who is 188 centimeters. That's the X, and the Y we're going to be predicting is the FEV1 for the male of that height. Now, what we saw from our last lecture is that with a positive correlation, the taller somebody gets, the uh, the the FEV1 increases. We see that taller people have higher FEV1 values, and we predicted maybe that's because lungs are larger in taller people. So what we assume is going to happen between these two examples is that the FEV1 for the shorter person is going to be lower than the FEV1 for the taller person. And we'll see when we evaluate these expressions. Okay, so let's look at the points again. We got the points of our scatter diagram. We've got the line of best fit going through the center of the points. Height is on the horizontal axis. FEV1 is on the vertical. 177 centimeters is a height that we can locate on the horizontal axis. And that's the input into our linear equation, the input x. So imagine that it's on the horizontal axis right around here, and we're going to put that x into our equation. We're going to get out the y, and that's going to be the answer to the question. That will be the FEV1 value. So let's start with the standard equation of a line, y equals ax plus b, and then enter underneath that the actual equation of our line, 0.0744x plus a negative 9.1904. So for the equation of the line, we keep the x as the variable, but when we are solving for a particular value for FEV1, we are going to let x be replaced with 177. So we're going to take our value of x and change it to 177, which means that this piece of the equation is going to involve multiplication. So we're going to be multiplying 0.0744 by 177. Multiply 0.0744 multiplied by 177, and then add a negative 9.1904. So we're going to get this answer. I'm going to jump to the calculator and show you what it is. Okay, so let's do the math right here. 0.0744 multiplied by 177 plus, and remember the negative key is to the left of the enter key down here, negative 9.1904. Okay. And this is our answer. This is our FEV1 answer or prediction for a male who is 177 centimeters tall. Okay, now because we are going to do the same exact kind of calculation for the next male who's 188 centimeters tall, let's do that right now on the calculator. Let's plug in 188 for x. So 0.0744 multiplied by now 188, and then do the same B part. 9.1904. Okay, and I expect this to go up because in a positive correlation, as x increases, y also increases. So I expect this to go up, and it has. Okay, so these are the two FEV1 values for the differing heights, 177 centimeters and then 188 centimeters. Okay, so our answer for the first question, 3.9784, and that is the estimated FEV1 value for a male who is 177 centimeters tall, 3.9784 liters. And the second piece was for a male who is 188 centimeters tall. That's our X input. Now, visually, you know that if 177 was here, 188 is to its right, and that's going to result in a higher FEV1 because as X increases, Y increases in a positive correlation. So when we plug this in, we did get a more positive or an increased value for FEV1, and it was 4.7968. Okay, so let's put this into words. The estimated FEV1 value for a male who is 188 centimeters tall is 4.7968 liters. Okay, so as X increased, 177 to 188, Y increased from 3 point whatever the other one was to 4.7968. Okay, so let's go back to the data. We made a prediction for a male who was 177 centimeters tall based on our linear equation. But if you take a look at the data, we have 3 males in our sample who are all 177 centimeters tall, but none of them have exactly the same FEV1 values as the prediction that we made when we plugged into our equation. So this is something that happens with linear regression. There are 3 males with heights of 177. None of them have FEV1s exactly like the one we got when we plugged into our equation, 3.9784. So regression analysis provides a predicted trend between 2 variables. It is not a perfect prediction for every individual. So when we got that graph, when we got that line among the points, not every point was on the line. And therefore, we're not looking to match every single person in the sample to a particular FEV1. It's impossible. The line is a prediction. It's supposed to predict a trend, and it's an estimate. It is not a tried and true prediction. So even if we have a relationship between height and FEV1, other factors can cause individual points to deviate from the predicted trend. So we're not always going to see exactly we can't always predict exactly what FEV1 could potentially be. There are other factors that contribute. So what other factors do you think could cause different values in FEV1 other than height? Okay, people of the same height may have different FEV1s. So what are the other factors that can contribute? So let's think about that for a minute. We're talking about how much air is exhaled in the first second after a maximum exhalation. So other factors that could be involved besides a person's height could include a person's age, their lung health and their lifestyle, etc., diet, exercise, things like this. So regression analysis provides us valuable insights, but it is not a definitive prediction for every individual. So we have to keep in mind that this is just an estimate. The regression line represents the best fit for the data capturing overall trend. However, individual variation around this line is expected and normal. The strength of the correlation coefficient influences how tightly the data points cluster around the line. So we know from the R value. A high correlation means points are close to the line, while a lower correlation means they are more scattered around the line. And actually, this is high but close to +1 or close to -1 would also be a tightly clustered points around the line. Lower correlation would be around 0. That would be a greater scattering around the line. Okay, so let's look at the concepts of interpolation and extrapolation. So this is the same height and FEV1 data that we've been using now from the last lecture. Let's look at the data range. So for height, the ranges of heights go from as low as 164 centimeters and they go up to 183.7 centimeters. So we have the shortest person in the sample and the tallest person in the sample. 177 is inside the range of the heights in our sample. So the predicted FEV1 for a height of 177, and that came out to be 3.9784, that predicted FEV1 is said to be interpolated. 188, that was the other value of x that we plugged into our regression equation, but it's outside the range of heights in our sample. The highest height is 183.7, so 188 is outside of that range. The value that we got when we plugged in 188 into our regression equation, 4.7968, that prediction is called an extrapolated prediction. It's outside, or it's the result of plugging in a value that is outside the range of x values. Okay, so what does it mean to be interpolated and extrapolated? Well, it does affect reliability. Regression models are more reliable for interpolation since predictions stay within the range of values from the data. So our regression equation is most accurate for heights between 164 and 183.7. It's most accurate for that range of heights. Outside of that range of heights, either below 164 or above 183.7, our predictions are less accurate, okay, or less reliable. Extrapolation can be uncertain when we're extending the model to a region we haven't collected data, which may involve different patterns or trends. So for that, it's values that are below 164 in height or above 183.7 in height. Extrapolated values could lead to inaccurate predictions about patient outcomes if applied beyond the data's scope. Okay, extrapolated FEV1 height for 188 centimeters is less accurate than the interpolated FEV1 for a height of 177 centimeters. So extrapolated is less accurate than interpolated. Okay, so 188 was extrapolated because it's outside of the range. 177 is interpolated because it's inside the range. So looking at our equation without any of the points, 164 is on the far left and 183.7 is on the far right of the x values that were used to construct the equation. And that results in extrapolated and interpolated. I'm sorry, that results in, where is it here? The interpolated piece. So 164 to 183.7 gives us a portion of the graph with FEV values that are in the interpolated range. This piece right here. Outside of that 183.7, or on the other side, outside of the 164 centimeters, we have the other pieces of the graph, which give us the extrapolated data. So we are going to recognize that the interpolated data is more accurate and the extrapolated data is less accurate, less reliable. Okay. Okay, so let's take a look at the coefficient of determination now. We've shown that we have a positive correlation between heights and FEV1 levels. But as we discussed, there are other factors that influence FEV1 that exist outside of our data. And we said it could be age, lung health, lifestyle, diet, fitness, etc. So let's look at age as a possibility and lifestyle and lung health. Okay, so these are three possibilities for factors outside of height that could influence FEV1. We have this measure called the coefficient of determination. The degree of influence that one variable has on another variable is found with a measure called the coefficient of determination. In this example, the coefficient of determination tells us the degree of influence that height has on FEV1. Okay, the degree of influence that height has on FEV1, and it's usually expressed as a percentage. Okay, the coefficient of determination is represented by R squared, and it measures the proportion of variation in the dependent variable that is influenced by the independent variable. How much of an influence does height have on FEV1? So we are going to find R squared, and then we're going to convert it to a percentage by multiplying by 100. So for example, if you looked at this pie chart, you could see the part in red is a portion, a percentage of the whole. And when we calculate our coefficient of determination, it will be some percentage. So let's say X percent, and factors outside would be considered the other percentage. We can say that that's the Y percent. Okay, so for height versus FEV1, the coefficient of determination measures the proportion of variation in FEV1 influenced by height. R squared is found using ln reg AX plus B and noting the R squared value in the output. That's when you have the raw data. If you don't have the raw data, you can simply square the correlation coefficient. So if you have R, like if it's given to you in a problem and you don't have the raw data, you could find the coefficient of determination by squaring that value of R that was given to you. Okay, so in our output on ln reg AX plus B, R squared is this line right here. We're going to take it to two decimal places. Here it would be 0.34 because we're going to round up since that 7 is 5 or greater. Sorry, we're going to take 4 decimal places. Let's take 0.3379. And then we're going to multiply by 100, and that's going to give us a percentage of 33.79%. Okay, so let's interpret this coefficient of determination, 33.79%. It suggests that there's some other influences on a person's FEV1 beyond height. Okay, the remaining 66.21%, and I'm getting that by subtracting from 100. 100 minus 33.79 gives 66.21. The remaining 66.21% of variation is due to other unexplained factors. They've not been provided to us in this problem. The unexplained amount is out of the scope of the problem. We can accept that there are other factors that contribute to the variable FEV1. We can hypothesize that age, health, lifestyle may play a part, but we don't have the data on these variables to actually give a definitive answer. So we have a percentage that explains how much of an influence height has on FEV1, but the rest of that percentage, the rest of the factors are unaccounted for and are outside of the scope of the problem. So to interpret the coefficient of determination, we're going to say that 33.79% of the variation in FEV1 is influenced by height. The remaining 66.21% might be due to unmeasured factors outside of the scope of this problem. And in general, that is how we are always going to measure a coefficient of determination and interpret it. We will state the coefficient of determination in terms of a percent, and we'll state what the dependent variable is, being influenced by the independent variable. And then we're going to state the remainder of the percentage, which is outside the scope of the problem. Okay, so let's take this example and do another one very similar to it involving physical therapy and gait speed. We've already talked about gait speed as a measure of somebody's walking speed. And in this example, we have some raw data that a physical therapist is using. They are conducting a regression analysis on gait speed hours, gait speed and hours of physical therapy. For the data here, for 10 patients, we're going to calculate the following. We're going to find the correlation coefficient and give an interpretation, that's R. We're going to find the coefficient of determination and give an interpretation, that's R squared. We're going to find the regression equation, that's y equals ax plus b. We're going to graph the scatter diagram and equation on our TI-84s. So I don't know what it looks like. I don't know if it looks like that or if it looks like that. I'm not sure yet. We'll see. And we're going to make a prediction. Predict the gait speed after 15 hours of physical therapy. And predict the gait speed after 30 hours of physical therapy. So let's recognize here that the independent variable, the variable that we are trying to change, the change that we are trying to make is in gait speed, but we are trying to influence it by changing the hours of physical therapy. So hours of physical therapy is our independent variable, and that is X. Gait speed depends on hours of physical therapy, so gait speed is Y. Okay, so we are going to go to the calculator, put all these values into two lists, and we're going to conduct a regression, correlation, and analysis and regression for all these parts. Let's go to the calculator. I'm sorry, before we go to the calculator, I just want to include one last question here. Which prediction is more accurate? The prediction for gait speed after 15 hours or the prediction for gait speed after 30 hours, and why is it more accurate? That is going to be a question of interpolation versus extrapolation. Okay, so let's go to the calculator's lists, and I have a lot of data in here from previous examples. I'm going to take out what's in L3 and what's in L4, and I'm going to put in this physical therapy gait speed example. So I'm going to put in X, those are hours of physical therapy in L3, and I'm going to put in gait speed into L4. Now the calculator just locked up on me. Just give me a second. Okay, so let's put in hours of physical therapy in here, L3. So I have 5, 8, 10, 12, 15, 18, 20, 22, 25, 28. And let's put in gate speed into L4. Okay, 0.1, 0.13, 0.16, 0.15, 0.18, 0.22, 0.25, 0.2, 0.27, and 0.30. Okay, the first thing I'm going to do is calculate the correlation coefficient to determine the strength of the relationship between hours of physical therapy and gait speed. Stat Calc number 4. My data is in L3 for the x values and L4 for the y values. Leave the rest blank and calculate. And my regression or my correlation coefficient is very strong, 0.9592. 0.9592. Okay. Also, I'm going to pull out from this screen my A, the A value that's going to be plugged in, that's going to be the constant in our equation, AX plus B. Pulling the A value out, we have 0.0081. And pulling the B value out, we have 0.0638. Okay, so we have A, B, R. And now for the first time, we are using R squared to answer a couple of questions. So let's pull out the R squared as well. 0.9201, and that gets converted to a percent. It'll be 92.01%. 0.9201 gets converted by multiplying by 100. So let's now interpret the meaning of those two things, the correlation coefficient and the coefficient of determination. So I'm going to jump to now the slideshow and interpret the meanings of these two things. Okay, so taking the correlation coefficient out, we have 0.9201. Okay, and I'm sorry, that's wrong. Let's fix this. I took the wrong values out. 0.9592. The strength of the relationship between hours of physical therapy and gait speed is 0.9592. That is a positive correlation. Okay, coefficient of determination. I accidentally swapped these. Let's fix this one. 0.9201. That would be this one right here. And turning that into a percent, we have 92.01%. 92.01% of the variation in gait speed, that's the y variable, is influenced by hours of physical therapy. That's the x variable. And let's fix this. It's not the remaining 4.08%. We're going to subtract 90, we're going to subtract from 100. We'll subtract 92.01 from 100. And that gives us 7.99. The remaining 7.99% is due to unexplained factors outside the scope of this problem. Okay, did I pull my regression equations out correctly? Let's make sure. Okay, we're good with the A and B. So let's go here. Okay, so our A 0.0081 is what we plug in over here. And our B 0.0638 is what we plug in here. So this is our finished regression equation. Okay, now let's plot that graph along with our points on our scatter diagram and let's see what we get. Okay, so I'm going to go into stat plot and oops, this is way off. So let me fix this. I'm going to turn this to the scatter diagram and have it point to L3 and L4. And I also want to take a look at, I think the other plots were on. So let me make sure I turn those off. Right, let me turn this one off. I'm going to turn number 2 off. Okay, and in y equals, let me just make sure that's good. Okay, in y equals, I'm going to put the equation that we just established, 0.0081 x plus 0.0638. Okay, ax plus b. And now I'm going to press zoom stat, and no, that's number 9. And now I've got my points and this regression equation graphed between them. So there would be a problem if I didn't see my regression equation properly, or if it was way off on the top or on the bottom of the points, that would indicate an error. Something, maybe I calculated something wrong. Maybe my regression equation is wrong. Maybe my points are plotted incorrectly. But when the points are around the line and the line passes through the points, through the middle of the set of points, then we likely are okay. So let me go back to the slideshow. Okay, so this is the picture that we got, and we confirmed it on our calculators. Okay, so let's make a prediction based on a value of x. So when x is 15, when we've put in 15 hours of physical therapy, what can we expect to see in gait speed? So let's plug in x equal 15 into our equation. So this is our linear equation. Let's plug in 15 for x. So that means over here we're going to be multiplying 0.0081 times 15. Okay, and when we evaluate this, when we evaluate this expression, we get a gait speed of 0.1853 meters per second. Okay, so we plug 15 in for x. When x is 15, we get out, that's 15 hours, we get out a gait speed of 0.1853. Now, let's also do the same thing for 30 hours of physical therapy. We're going to let x be 30 now. Using the same equation, but letting x be 30, let's evaluate this expression on the calculator. So instead of me going back to the calculator, you now see how I've done this. You plug in 0.0081 multiplied by 30 plus 0.0638, and our gait speed, because this is a positive correlation that increases from left to right, as x increases, y increases. So we know if we're going to increase x to 30, we know that the y that we get out is also going to be increased. It's going to be more than 0.1853, and it comes out to be 0.3068. Okay, so there's our increase. We have a faster gait speed for more hours of physical therapy. So now we have to ask about interpolation and extrapolation. Let's look at our data again. And we have to decide which prediction, gate speed after 15 hours or after 30 hours, is more accurate and why. We have to look at our data and look at the range of X values. So maybe we have to go back here. Let me go back to the data. Look at the values of X. Okay, X goes from a low of 5 to a high of 28. So 15 is part of the X values. 15 is in that range, and therefore the value that we got when we plugged in X equal 15, the value for gate speed was interpolated. Now X equal 30 is outside of the range. See that the end is 28, so 30 is outside the range. The gate speed value that we got when we plugged in an X equal 30 is extrapolated because it is outside the range. The one that is most predictable, or the one that has got the more accurate prediction, is the one for 15 hours, because it is an interpolated prediction instead of extrapolated prediction. 0.1853 after 15 hours is more accurate because it is interpolated. 0.3068 after 30 hours is extrapolated outside of the range of data, and that makes it less predictable. Okay, so let's finish this lecture with a discussion on correlation and causation. Correlation is not causation. Correlation between hours of physical therapy and gait speed indicates that we have an association. As one variable changes, that is physical therapy, the other changes, gait speed. And it changes in a predictable way. In this sense, it goes up. As we increase physical therapy, gait speed also increases. However, it doesn't tell us why this relationship exists or if physical therapy directly causes an increase in gait speed. Okay, it does not tell us that we have causation. For physical therapy to be considered a causal factor for gait speed, we would need evidence showing that an increase in physical therapy directly causes an increase in gait speed. To establish that kind of proof, to establish causation, you need to conduct a controlled experiment or randomized trial. And when you do this, when you do a controlled experiment, you are isolating the effect of therapy hours from other variables. So the only variable that is being affected in a controlled experiment are the hours of therapy. And ideally, when you do this kind of experiment, you have a control group and a treatment group, and you carefully control all other factors and make sure nothing is changing except physical therapy and hours of physical therapy. So that is a very carefully controlled experiment where you can show causation, but a correlation alone does not show that. So there are other factors that could contribute to an increase in gait speed that are outside of this data and perhaps may have had an influence on the increase. Patient motivation. Patients who are motivated might both attend more therapy sessions and work harder, leading to faster improvements. Baseline health. Patients with better initial health might naturally improve more quickly and therefore may attend therapy more regularly. Thus, even though physical therapy hours and gait improvement show that they are correlated, therapy hours alone may not be the only or direct cause of improvement. Okay, we have other factors that are possible contributors, and we can't say that physical therapy causes the improvement in gait speed. To prove that physical therapy directly causes the increase in gait speed, all other variables need to be removed. We have to remove patient motivation and baseline health. And conduct a controlled randomized experiment where the only variable that is being manipulated is the hours in physical therapy. Okay, so here, sorry, I didn't intend to that to happen. Just give me a second. Okay, so correlation is not causation. Regression. Regression helps us model relationships between variables, but it does not prove causation. Finding a high correlation coefficient between therapy hours and gait speed does not confirm that therapy alone is the only factor driving improvements. Correlation and regression analysis help us identify patterns, but not cause and effect relationships. So if we did, if the correlation showed that we do have an association, it may give us reason to want to conduct a controlled experiment and possibly prove that there is a cause and effect relationship here. But it is not the end all decision maker on whether or not X causes Y. And that is where we're going to end with this double lecture on linear regression and correlation. It's just an introduction to the topic. You can go a lot further with it, but this is where we're going to keep it in this semester. It's just an introduction. And hopefully, by the end of the semester, you will see where this fits into everything. So thanks for joining me today. I'm going to see you at the next lecture. Let me know if you have any questions. Bye.